Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 6, Learning to Read Phi, the Art of Unwrapping. Remember the language we are learning. There is one field, Phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When Phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how Phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of Phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. Welcome to Book 10.1, Language Fluency. From scattered data to living Phi sentences. We have just laid the foundation of Episode 10, understanding that engineering is coherence management, that we work with the universe's resonant pathways, not against them. Now we enter the first practical workshop. If the goal is to speak and program the universe, we must first learn to read its sentences. We cannot align with what we cannot see. We cannot build on what we cannot measure. So today, in part 10.1.1, we learn the first and most fundamental skill of a Phi-literate civilization: how to look at a mess of raw, noisy sensor readings and see the underlying phase field. How to listen to the universe's faint, garbled whispers and hear the clear tone of Phi. Our anchor image for this journey is a music studio's mixing desk. You, the listener, are the sound engineer. Before you is a panel of glowing dials, sliders, and meters, all showing raw waveforms, messy, clipped, full of static. Your job is not to create new music yet, but to clean the signal. To isolate the pure note from the noise, to see its precise shape, its rhythm, its location in stereo space. You are learning to read the score from which the symphony is played. Scene: the first glimpse of a pattern. Imagine you are in a quiet laboratory. Before you is a simple machine, a laser interferometer. It splits a single pure laser beam into two paths. One beam travels a fixed distance and bounces back. The other beam strikes the surface of a thin metal plate, a diaphragm that vibrates subtly, like a drumhead responding to a distant sound, and then returns. The two beams meet again. Where they are perfectly in phase, peak meets peak, they add together, creating a bright spot of light. Where they are perfectly out of phase, peak meets trough, they cancel, creating darkness. Your sensor, a camera or a photo detector, doesn't see Phi. It doesn't see phase at all. It sees only the result of that interference: intensity, brightness. A number between 0 and some maximum for each pixel in your camera. This is our starting point. A grid of numbers. Bright here, dim there, a grainy, speckled pattern of light and dark fringes. It is beautiful, but it is a cipher. It is the universe giving you a coded message in a language you do not yet know how to read. The vibration of the plate has imprinted a signature onto Phi, and that signature has been stamped through interference onto this pattern of light. Your job is to work backwards. From the stamp, deduce the signature. From the intensity, reconstruct the phase. This is the art of phase unwrapping. It is the skill of turning a noisy, ambiguous map of brightness into a confident, continuous map of Phi, complete with a clear statement of what we know and, crucially, what we don't know. Let's step up to the mixing desk. The raw signal, a world of shadows and echoes. You look at your first dataset. It's a single snapshot from the camera. You see a series of dark and bright bands, interference fringes. Each bright band corresponds to a region where the path difference between the two laser beams is an integer multiple of the laser's wavelength. Each dark band is where they are half a wavelength out of step. If the plate were perfectly flat and still, the fringes would be straight, parallel lines. But the plate is vibrating. The fringes bend and swirl. The bending tells you that the surface of the plate is not flat. its height varies, changing the path length of the beam that hits it. The amount of bending at any point is proportional to the local phase shift phi at that point. But there's a problem, a fundamental, beautiful ambiguity. Your intensity reading, I, is proportional to the cosine of the phase difference. I is the cosine phi. The cosine function is periodic. Cosine phi is equal to cosine phi plus 2 pi is equal to cosine phi plus 4 pi, and so on. If your sensor tells you the intensity corresponds to a phase of, say, 0.1 radians, that intensity is identical to what you would see for a phase of 0.1 plus 2 pi, or 0.1 plus 4 pi, or 0.1 minus 2 pi. Your data gives you phi, but only modulo 2 pi. It gives you the phase wrapped onto a circle. It tells you the hand of a clock points to 5 minutes past, but it doesn't tell you if it's 12:05, 1:05, or 11:05. It tells you the note, but not which octave. This is our first coherence gate. Think of coherence here as the readability of the signal. Can we trace a path through this wrapped phase map and decide unambiguously which 2 pi cycle we are in at each point? If the phase changes smoothly and slowly from point to point, if the signal is coherent, then we can assume that neighboring pixels differ by less than pi. We can unwrap by adding or subtracting 2 pi whenever we see a sudden jump from near plus pi to near minus pi, stitching the continuous phase landscape back together. But if the signal is noisy, if the phase is changing too rapidly, if there are defects or tears in the field, then this path becomes ambiguous. Different paths through the data might lead to different unwrapped results. This is dissonance in our reading. The message is garbled. If coherence breaks, we stop. If coherence returns, we continue. Our first operational metric for coherence in reading is local integrability. Pick any two nearby points in your measured wrapped phase map. Choose two different paths between them. If you add up the tiny phase differences along each path, integrating the gradient, do you get the same total phase difference? If yes, the field is locally integrable. It is coherent enough to have a unique unwrapped solution. If no, if the answer depends on the path you take, then the field has a topological defect, a vortex, a source at its heart. Or the noise is so high that the concept of a single smooth phi is meaningless here. Our safety rail is born here, at the very first step. Uncertainty. Any reconstruction of phi must come with an explicit, pixel-by-pixel map of its own uncertainty. We must not only say phi is 2.1 radians here, but phi is 2.1 plus or minus 0.05 radians here. And in regions of high noise or near defects, that uncertainty must blow up, signaling, here be dragons, do not trust this reading. The unwrapping algorithm, walking the landscape. Let's make this concrete. You are the sound engineer, and the wrapped phase map is a strange, repeating terrain. It's like a mountainous region where the altitude is only recorded modulo 10 meters. You see a ridge that goes from a height of 9 meters up to 1 meter? No, that's impossible. It must have crossed the 10-meter boundary. So you add 10 to everything beyond that point. Now the ridge climbs smoothly from 9 to 11 meters. You continue this process, walking across the entire map, adding or subtracting 2 pi, our 10-meter unit, whenever you encounter a jump larger than a threshold. This simple path-following unwrapping is our first tool. But it has a weakness. It depends on the path you take. Start unwrapping from the top left corner and proceed row by row. And you might get a different result than if you start from the center and spiral outward. Noise can trick the algorithm into seeing a jump where there isn't one, or missing a jump where there is one, causing an error that then propagates across the entire map. This leads us to our prediction spine. Prediction 1. If our sensor signal-to-noise ratio, SNR, is high, if the signal, the coherent interference pattern, is strong and clear compared to the random camera noise, then the uncertainty in our reconstructed phi will shrink. Specifically, it will shrink proportionally to 1 over scratch root of SNR. Double the photons captured, and your phase uncertainty decreases by a factor of scratch root of 2. This is not magic, it's the statistics of light. A clearer signal gives a clearer reading. Prediction 2. If our unwrapping is correct, it should be self-consistent. Take two independent subsets of the data, say 2 consecutive snapshots in time, or analyze the odd-numbered pixels and the even-numbered pixels separately. Reconstruct phi from each subset. The two reconstructions should agree with each other within their combined error bars. If they disagree wildly, something is wrong with our method or our assumption of a single coherent field. Prediction 3. The ultimate test. We will build a digital twin. This is a software sandbox, a perfect simulated version of our experiment. We will program it with a known ground truth phi pattern, perhaps a simple wave rippling across the plate. We will then simulate the laser interference, add realistic synthetic camera noise with a known statistical profile, and generate a fake camera image just like our real one. We then feed this synthetic data into our unwrapping algorithm. If our algorithm is good, it should recover the original known phi pattern within the uncertainty bounds we predicted from the simulated noise level. This is our calibration crucible. Now let's look at our falsifiability thread. Falsifier 1. Imagine we have beautiful high SNR data from a seemingly simple system. We apply two different, well-justified unwrapping algorithms. Perhaps one that follows rows and one that uses a more global optimization technique. If these two methods produce phi maps that are fundamentally irreconcilably different, their disagreement is far larger than their calculated error bounds, this is a crisis. It suggests a core assumption is false. Perhaps for this system, there is not a single coherent phi field underlying our measurements. Perhaps the light is partially coherent, or there are multiple overlapping fields we haven't accounted for. Our simple model breaks, and we must go back to a more fundamental description. Falsifier 2. Simpler, but equally important. If we consistently find that our real-world measurements violate the uncertainty bounds predicted by our twin-calibrated noise model, if the errors are always larger than we said they could be, then our noise model is wrong. We are missing a source of noise, vibration, thermal drift, or mischaracterizing its statistics. We must improve our model or our hardware. Triunity in the act of reading. Let's pause and feel the triunity here, alive in this first act of reading. We are measuring a spatial pattern, the phi of XY map across the plate. This is our space echo, the texture, the gradients, the bending of fringes. But to understand that map, we must consider its temporal stability. Is the pattern steady or flickering? We might take multiple snapshots to average out noise, which is a time echo, rhythm, sequencing, stability over duration. And from the spatial gradient of phi, we can infer the local motion of the plate surface, its tilt, its slope. This derivative is our motion echo, the implied drift, the flow of the surface shape. We are not measuring three separate things. We are asking one question, what is phi? And its answer casts these three shadows simultaneously. A good reading captures all three echoes in harmony. The coherence budget for reading. Now we formalize our coherence budget for this task. Before we even attempt to unwrap, we must assess if we have the capital to do so. The budget here is defined by signal-to-noise ratio and spatial coherence length. 1. This is our cache. We need enough signal photons to overcome random noise. Our budget dictates. For a target phase precision of delta phi, we require an SNR of at least 1 over delta phi squared. If our measured SNR is below this, we cannot afford the reconstruction. We must earn more capital by integrating for longer, using a brighter laser, or a more sensitive camera. 2. Spatial coherence length. This is our credit limit. It's the distance over which the phase remains correlated. If we try to unwrap across distances larger than this coherence length, our algorithm will fail. It's like trying to follow a conversation in a roaring crowd. The words are lost beyond a certain distance. Our budget says the unwrapping path between any 2 points must be shorter than the measured coherence length. If the feature we want to see is larger than this, we cannot read it in one glance. We must break it into smaller, coherent windows. Our coherence gate is the check after unwrapping. We don't just look at the pretty phi map. We run a battery of tests. Path independence test. Unwrap the same data along several different randomly chosen paths. Do the results agree within the calculated uncertainty? If variance between paths is high, we fail. The data is incoherent. Residual check. Take our reconstructed phi, simulate what the camera should have seen, calculate cos of phi, and compare it pixel by pixel to the actual camera image. The differences, the residuals, should look like random noise. If they show structured patterns, lines, swirls, blotches, our reconstruction is missing something. We fail. If we fail the coherence gate, we hit the rollback trigger. We do not proceed. We do not use this faulty phi map to calculate derivatives, make predictions, or feed into control systems. We contain the error by flagging the entire dataset or region as low confidence. We damp our ambition. We scale back our goal to a simpler question. We revert to stating only what we know for sure. The intensity pattern was X, the wrapped phase is Y, the coherence length is Z. A full phi reconstruction is not justified here. We have hit the boundary of our licensed window, the regime where our method is validated. We must now either improve our hardware, get a better budget, or restrict our claims to stay within the window. Lanterns across scales, the universal need to unwrap. This is not just about laser fringes on a metal plate. The need to unwrap phi from ambiguous data is a universal pattern. A biologist using a phase contrast microscope sees halos around cells. Those halos are interference fringes. To get a true quantitative measure of the cell's thickness and density, she must unwrap that phase signal. Her coherence budget is the stability of her light source and the transparency of her sample. Satellite-based radar, INSAR, measures the distance to the Earth's surface with incredible precision. Between two satellite passes, an earthquake shifts the ground. The radar sees a shifted interference pattern. Unwrapping this pattern reveals the exact map of ground displacement, down to centimeters. The coherence budget here? The landscape must not have changed too much, for example, from vegetation growth, between passes, or the speckle pattern decorrelates, and the phase becomes unreadable. In radio astronomy, very long baseline interferometry, VLBI, combines signals from telescopes across the globe to create a virtual Earth-sized dish. The data from each telescope is a complex signal with a phase. To combine them, astronomers must solve for the unknown atmospheric delays that affect each telescope's phase, a global unwrapping problem. Their coherence budget is the stability of the atomic clocks at each site and the models of the atmosphere. In each case, the core challenge is the same: a cyclic, ambiguous measurement, the need for a smooth, continuous phase field, and a coherence budget that determines whether the puzzle can be solved. The mixing desk is everywhere. The ethics of measurement, honesty in uncertainty. Here, in this first skill, we encounter the foundational ethic of Episode 10 Engineering: intellectual honesty about limits. It is unethical to present a reconstructed phi map without its uncertainty field. It is a lie of omission. It invites downstream users, perhaps an engineer designing a control system, or a scientist testing a theory, to place false confidence in your numbers. They might take your smooth-looking map, calculate a derivative, and proclaim a discovery, not realizing that the derivative amplifies noise and that the result is built on sand. The safety rail. The reconstruction must be tagged with an uncertainty field. Any downstream use that does not propagate these errors is invalid, is not bureaucracy. It is the moral equivalent of a building code. It prevents catastrophic structural failure in our edifice of knowledge. Power without coherence is self-destruction, and the first step toward coherence is knowing precisely where you are incoherent. The recognition skill, seeing the need to unwrap. So how do you, as a practitioner, recognize when you are in the domain of this skill? You will see cyclic repeating patterns in your data. interference fringes, moire patterns, wrapped angles on a compass. Any measurement that gives you a value modulo some fundamental period. And you will have a need for continuity. You need to know not just the local value, but how it connects to its neighbors to form a whole. The moment you ask, but what's the total change from here to there, you have entered the art of unwrapping. If you look at a dataset and think, the jumps here are artifacts, the real quantity should be smooth, you are thinking like a phase unwrapper. The digital twin, our first sandbox. Let's return to our studio. Our mixing desk has a special monitor, the digital twin display. For our vibrating plate experiment, the twin is a physics simulation. We define the material properties of the plate, the frequency and amplitude of the sound driving it, the laser wavelength, the camera pixel size. It generates the true phi XYT. It then simulates the physics of interference and camera noise to produce synthetic data that is indistinguishable statistically from what a perfect experiment would yield. This is our sandbox. Before we ever trust our algorithm on precious, hard-won real data, we beat it to death in the twin. We create known, challenging phi landscapes, steep gradients, sudden cliffs, swirling vortices, topological defects. We add different types and levels of noise. We run our unwrapping algorithm. Does it recover the truth? This process does two things. First, it validates our algorithm. If it works in the twin, it has a chance of working in reality. Second, and more importantly, it calibrates our confidence. It shows us, empirically, what level of SNR is needed to achieve a desired precision. It maps out the boundaries of our licensed window. For a plate vibrating at less than 1 kHz, with our current laser power, we can reliably reconstruct phi with 0.1 rad precision. Beyond that, all bets are off. The twin turns engineering from an art into a predictive science. It is our coherence wind tunnel. A measurement scene, passing and failing. Let's witness our measurement scene from the roadmap. Scene: a calibrated laser interferometer measuring the surface of a vibrating plate. The reconstructed phi map shows a smooth, wave-like pattern, like ripples on a pond. The uncertainty field, a companion map, shows low, uniform uncertainty in the bright, high-intensity regions. In darker areas, uncertainty gracefully increases. Most importantly, if you use 3 different unwrapping algorithms, row by row, quality-guided, minimum cost flow, they all produce essentially the same phi map, differing by less than their stated uncertainties. The signal is coherent. The message is clear. The output is chaos. Different algorithms give wildly different pictures. One produces a smooth wave, another produces a wave with a giant cliff through the middle. A third gives a patchwork of unrelated segments. The uncertainty field is large and uniform, or worse, it is small in areas where the algorithms disagree. A sure sign our uncertainty estimation is broken. This failure shouts, the data is noise-dominated, the coherence budget is exhausted, do not proceed. The fail state is not a disappointment, it is a vital piece of information. It tells us to stop, to improve our hardware, to reduce vibrations, to get a better laser. It enforces discipline. The path forward, what this skill unlocks. This first skill, learning to read phi, is the root of the master tree for episode 10. It has no dependencies because it is where we begin. But from this root, everything grows. It enables all measurement. Book 10.2. If you cannot read phi, you cannot build better sensors to measure it. You cannot measure its derivatives, omega and k, with confidence. You cannot hope to detect topological defects, which are singularities in the phi landscape. It enables all interpretation. Part 10.1.2. Once you have a clean phi map, you can start to recognize common clauses, the wave clauses, the jet clauses, the defect clauses. You can begin to understand the sentences the universe is speaking. Without this skill, you are illiterate. You have a box of intricate tools, but you cannot read the manual. You are deaf to the universe's most fundamental language. Zenodo and the full picture. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The equations there formalize the cost functions that global unwrapping algorithms minimize. They define the Cramer-Rao lower bound, the theoretical limit of how well you can estimate phase given a certain noise level, the ultimate coherence budget set by physics itself. They turn the art we've described into a rigorous computational discipline. Return to the phi. Let us zoom out. We have taken our first step into the workshop. We have learned to take the raw cyclic data from the world, the intensity, the modulo 2 pi measurement, and, when coherence permits, unwind it into a continuous map of the fundamental field, phi. We remember, there is only one field. Its value, phi, is not directly seen. It is inferred from relationships, from interference, from comparisons. Our first act of engineering is an act of careful, humble inference. We are not imposing, we are listening. We are cleaning the signal so we can hear the true note. We have established our first non-negotiable discipline, the pairing of every claim with its uncertainty, and the obedience to coherence gates. If the signal is incoherent, we do not pretend otherwise. We state our ignorance and seek better conditions. This is the foundation of all that follows. From this stable root, we can now grow. We can learn to not just read the static shape of phi, but to read its verbs, its omega and k. We can learn to recognize the words and grammar of its sentences. But that is for the next part. Closing. So, picture yourself back at the mixing desk. The raw waveforms are still there on the screen, but now you know what to do. You reach for the noise reduction filter, increasing SNR. You adjust the time averaging, improving temporal coherence. You run the unwrapping algorithm and watch as the chaotic repeating pattern resolves into a single, clean, continuous curve, the true shape of the phase. A confidence interval, a pale band, hugs the curve, showing its uncertainty. You have transformed noise into a readable signal. You have just learned the alphabet's first letter. You have learned to see phi. This is part 10.1.1, Learning to Read Phi, the Art of Unwrapping. It is the root of Book 10.1, Language Fluency, and the first practical step in Episode 10's journey from passive observers to literate engineers of reality. In our next session, we will take this clean phi map and start to understand what it is saying. We will learn to recognize the common clauses, the nouns and verbs, in the universe's endless story. We will move from seeing the letters to understanding the words. Remember, one field, phi, with its infinite echoes in time, space, and motion. Our journey has just begun, and already we have gained the power to see the world's deepest layer. Salam, and peace be upon you.